Welcome back to the deep dive. Today we are taking a sledgehammer to a very common misconception. I think most of us, when we use something like ChatGPT or Gemini, assume that when we upload a photo, the AI just looks at it. Like, it has eyes, it sees a dog, it knows it's a dog. Simple,
It
right?
feels intuitive because biological vision is so effortless for us. We open our eyes and the world is just there.
Right.
So we assume the machine does the same thing.
Exactly. But looking at the engineering breakdown we have today, specifically focusing on a system called InternVL, that assumption is completely wrong. We aren't just looking at pretty pictures today. We are looking at the architecture of machine perception. We're going to find out how engineers actually bridge the gap between raw pixels and human language. And honestly, the fact that it works at all is kind of a miracle.
It really is. And the source material you mentioned, the InternVL engineering blueprint, is essentially a masterclass in how to build a production-ready vision language model, or VLM. That's not just theory. It details exactly how you build a machine that doesn't just recognize a cat, but understands the context of the cat, reads the text on the cat's collar, and can answer complex questions about the background.
So we're moving from just seeing to understanding. What
Yeah.
distinguishes a VLM from just a standard image classifier?
A massive difference. A classifier says cat. A VLM says this is a tabby cat sitting on a mid-century modern chair looking anxious because there's a vacuum cleaner in the corner. It connects vision to reasoning. It bridges two completely different worlds.
Let's get into that bridge. The first thing the source material highlights is this fundamental disconnect. They call it the modality gap. To me, this sounds like the core problem of the whole field. Why is it so hard to get text and images to talk to each other?
It is the original sin of multimodal AI.
Yeah.
You have to understand, these models are trying to combine two things that fundamentally, well, they hate each other. On one side, you have computer vision that deals in continuous signals.
Continuous signals, meaning what exactly?
Think of a wave. Light intensity, gradients, pixel values, spatial relationships. It's analog in a sense. It flows. A pixel can be slightly lighter or darker, and it changes the data smoothly.
Yeah. And on the other side, you have the language model.
Right, and LLMs deal in discrete sequences, words, tokens, grammar.
Yeah.
It is symbolic. It's rigid. A pixel can be slightly lighter, but a word is either dog or log. There is no halfway point.
So you have one brain thinking in fluid waves of color and shape, and another brain thinking in rigid dictionary definitions.
Precisely. They speak completely different languages. So the engineering goal, as shown in the InternVL architecture, is to build a unified embedding space.
The diagram in the source shows a literal bridge connecting a vision encoder on the left and a text encoder on the right.
That's a projection layer. In the InternVL architecture, and frankly in most modern VLMs, you have that vision encoder digesting the image and the text encoder digesting the prompt. The projection layer is basically a mathematical translator.
Is it just translating image to text?
It's more abstract than that. It projects the visual features into a shared mathematical space. Think of it this way. The model doesn't turn the picture of a cat into the word cat. It turns the picture into a complex vector, a string of numbers that sits in a specific spot in a multidimensional map. And the goal is to force the word cat to sit at that exact same coordinate.
So when the math aligns, the model understands?
Exactly. If the vector for the image and the vector for the text overlap, the bridge is built.
Okay, so we've built the bridge, but having a bridge doesn't mean traffic flows. You have to teach the model how to use it. The source material lists 3 very specific learning objectives. This part felt like the actual curriculum for the AI.
It is. You can't just throw data at it. You have to give it tasks. The first one is the most famous, contrastive learning. You'll often hear this associated with CLIP models.
This sounded to me like a high-speed game of matching. Or maybe dating?
A bit like Tinder for data, actually. You take a batch of images and a batch of captions. You mix them up. The model's job is to pull the correct pairs together, maximize their similarity, and push the mismatched pairs apart.
So it learns that snow usually goes with white pixels and grass goes with green pixels.
Right. And this is crucial for what we call zero-shot recognition, because it learns the concept of snow, not just a specific picture of snow. It can recognize a snowy mountain it's never seen before because it understands the alignment between the visual pattern and the word.
Okay, that's objective 1, matching. The second one seems a bit more detective-like, masked modeling.
This is where it gets clever. Contrastive learning is great for the big picture, but it can be lazy. They might look at a photo of a kitchen, see a fridge, and say kitchen. It ignores the details on the counter.
So how does masked modeling fix that laziness?
It blinds the model. It takes the image and literally blacks out random patches. Or it takes a text description and blacks out words. Then it forces the model to reconstruct the missing pieces.
So if I show it a living room but I black out the sofa, the model has to look at the coffee table, the rug, the angle of the TV, and deduce there must be a sofa here.
Exactly. It forces the model to learn structure and context. You can't just memorize the image if half of it is missing. You have to understand the relationships between objects. If it can rebuild the image from memory, it truly understands the scene.
That makes sense. It builds a deeper intuition. And the third objective.
Autoregressive learning.
That's a mouthful.
It's just a technical term for next token prediction. This is the engine that drives ChatGPT. It predicts the next word in a sequence. But in a VLM, it's conditioned on the image.
So this is the part that allows it to write a caption.
Yes. You feed it the visual embedding, the mathematical vibe of the image, and it starts predicting. A robot is painting. This capability is what unlocks visual question answering. You ask, what is the robot doing? And the model uses that predictive engine to generate the answer based on the visual cues.
So we have the bridge, and we have the training curriculum. But here is where the InternVL paper throws a wrench in the gears. They identify a massive flaw in how previous models were built. They call it the scaling bottleneck.
This is the key insight of this specific architecture. If you look at the landscape before InternVL, there was a huge asymmetry.
Right, I was looking at the parameter counts in the source. You'd have these massive language models, the brains, with 7 billion, 13 billion, even 70 billion parameters, but the eyes, the vision encoders, were tiny.
Exactly. Most were relying on standard CLIP models, which are maybe 300 million parameters.
That's a huge mismatch. It's like hooking up a supercomputer to a webcam from 1998.
That is a perfect analogy. Or like putting cloudy, scratched sunglasses on Einstein. The brain is capable of incredible reasoning, deep philosophy, complex logic. But the visual signal coming in is compressed, low resolution, and simplistic. The model is effectively visually impaired.
So the InternVL solution seems obvious, but I imagine it's hard to execute. Just make the eyes bigger.
Scale the vision. That's their motto. They swapped out those tiny encoders for a monster called InternVT6B.
6 billion parameters, just for the vision part.
Just for the eyes. That is nearly the size of the language brain itself.
Why hasn't everyone done this? Is it just expensive?
It's incredibly computationally expensive to train, but the paper argues it's necessary. By scaling the vision encoder to 6 billion parameters, the visual signal becomes just as rich, nuanced, and complex as the language processing. They connect this massive eye to the brain using a very simple connector.
I noticed that they use an MLP projector. The source described it as lightweight.
And that's a specific design philosophy. If your eye is massive and smart, and your brain is massive and smart, you don't need a complicated bridge. You just need a simple pipe.
So you've got this massive beast of a model, 6 billion parameterized, 20 billion parameter brain. How do you train that without it collapsing? The slides describe a progressive alignment strategy.
You can't just turn it all on at once. It's like teaching a human. You don't start with philosophy. You start with A is for apple.
So walk me through the stages.
Stage one is that contrastive pre-training we talked about. Just getting the vision and text representations to look at each other. This is purely about aligning the raw data using massive data sets.
Just the matching game. Dog equals dog picture.
Right. Stage two is incremental pre-training. This is where they actually hook up that MLP connector to the language model. They feed it interleaved data articles with photos, textbooks with diagrams. This unlocks the ability to do visual question answering.
So now it can talk about what it sees.
But it's robotic, it's factual. That leads to stage three, supervised fine-tuning. This is where they use instruction data sets, carefully curated examples of helpful dialogue to make the model behave like a human assistant.
This is the polish. This is what makes it polite and conversational.
Exactly. It turns a raw prediction engine into a product.
Okay, I want to pivot to a practical problem I run into constantly. I use these tools to read documents sometimes. I upload a picture of a receipt or a crowded street sign, and half the time, the AI fails. It misses the small text. It hallucinates numbers.
That's the resolution issue, and it's a physical limit of how these models are usually built. Standard models squish every image into a fixed square, usually 224 by 224 pixels.
224 pixels, that's a postage stamp.
It's tiny. If you take a 4K photo of a contract and squash it down to 224 pixels, the text literally disappears. It becomes noise. The model isn't missing the text physically isn't there anymore in the data it sees.
So how does InternVL fix this? Because the source claims high performance on OCR optical character recognition.
They use dynamic tiling.
It sounds like they're cutting the image up.
Correct. Instead of squashing the image, they cut it into high-res tiles, each 448 by 448 pixels. And it's dynamic. It can use anywhere from one tile for a simple icon up to 40 tiles for a complex, high-res document,
So it scans the image like a human reading a page. Top left, top right, scroll down.
essentially. It feeds these tiles in as a sequence. But, and here's the potential trap, if you cut a picture into 40 pieces, the model might lose track of the whole. It sees a nose, an ear, a tail, but it might not realize it's looking at a dog because the pieces are separated.
Right, it loses the forest for the trees.
So the engineers added a global thumbnail. They send in the high-res tiles and a low-res version of the entire image simultaneously.
That is such a smart, practical fix. It gets the context from the thumbnail and the detail from the tiles.
It completely solves the resolution bottleneck.
Yeah.
This is why the benchmark scores for reading text and analyzing charts skyrocket with this model.
Now, we've talked about static images, but the world moves. The deep dive sources also cover InternVL too. How does this architecture handle video? Because video is just a lot of images, right?
It is, but the computational load explodes. And you introduce a new dimension, time.
The source used the term spatiotemporal coherence.
Fancy engineering speak for understanding how things change over time. But what's fascinating about InternVL 2 is the input strategy. It uses a multi-stream input.
Meaning it's not just looking at the video frames.
No, it's ingesting the video frames, the audio waveforms, the speech transcripts, and textual semantics all at the same time.
So it's hearing the explosion, seeing the fire, reading the subtitles, and analyzing the metadata all at once.
Yes, and they train it using a joint embedding space. They force the audio of a dog barking, the video of a dog, and the word dog to all map to the same mathematical point.
So if it hears a bark but the video is blurry, it still knows dog.
Exactly, it's robust.
Mm.
And then finally, they use that next token prediction again. This allows it to do open-ended reasoning, like, why is the person in this video crying? It uses the visual cues, the sad music, and the dialogue to answer.
That is incredible. But I have to bring us back to Earth. Even with this super brain and super eyes, we run into a problem that is purely human. The interface.
Ah, the prompting bottleneck.
This drives me crazy. You have this billion-dollar supercomputer, and if I type "show me the cat," it works. But if I type "show me a cat," the result changes. The source gave an example where adding the word texture to a prompt boosted accuracy significantly.
It's incredibly brittle. These models are sensitive to specific keywords that might have appeared in their training data. Manual prompt engineering, guessing which adjectives the robot likes, is inefficient. You can't build a reliable product if it breaks because you forgot the word A.
So how do engineers fix this? I don't want to spend my life guessing the magic password to get the AI to work.
They automate it. The source outlines two really distinct solutions. The first is called COOP, or differentiable prompt learning.
Differentiable prompt learning. Let's break that down.
Okay, normally you handwrite a prompt like a photo of a class. In COOP, the system replaces those hard-coded words with continuous learnable vectors.
Learnable vectors, so math placeholders.
Exactly. Imagine a set of variables, $, V2, V33, that feed into the model right before the class name. The model doesn't read English words there. During training, it adjusts those variables to find the mathematically optimal question to ask itself.
So the model is effectively whispering to itself in a language we can't hear, just to focus better.
That's a great analogy. It finds the perfect vector that represents the concept of the prompt. Rather than relying on our messy, ambiguous human language, it automates the word search.
That is wild. And the second solution?
TPT, or test time prompt tuning.
Test time implies it happens right when I'm using it.
Yes. This is adaptive optimization on the fly. Let's say you give it a weird, blurry image it's never seen before. The model generates multiple augmented views of that image. Maybe it rotates it, zooms in, flips it.
It's trying to get a better look.
It's checking its own consistency. It runs the prediction on all those views and checks if the answer is the same. It tries to minimize entropy or uncertainty.
So if it thinks it's a cat in one view but a dog in another, it knows it's confused.
Right. So it tweaks its prompt vectors in real time right there during the test until its confidence across all those views aligns. It effectively self-calibrates to the specific image you just uploaded.
Without any human intervention.
Zero. It adapts to the data on the fly.
So putting this all together, we have the massive 6 billion parameter eyes. We have the dynamic tiling to read the fine print. We have the automated prompting to fix our bad questions. Does it actually work? What's the scorecard?
It's impressive. They benchmarked InternVL against 32 generic visual linguistic tasks. And thanks to that massive vision encoder, it closes the gap with commercial APIs.
I saw the charts comparing it to GPT-4V and Gemini.
It approaches or even exceeds them in very specific hard areas like OCR and MathVista, which involves visual mathematical reasoning.
Visual math, like looking at a geometry problem and solving it.
Exactly. That requires precise detail and complex logic. That is the direct result of scaling the eyes to match the brain. If you can't see the angle clearly, you can't solve the proof. It's also using something called OVDETR for object detection.
Right, open vocabulary object detection.
This is cool. They use prompt ensembling. They generate about 63 different ways to say there's a dog or a photo of a dog, average them out, and create a robust classifier to find objects that hasn't explicitly been trained on.
So to wrap this up, if we look at the unified VLM architectural pattern presented in the final slide, what are we really seeing? This feels like the blueprint for the next few years of AI.
I think so. It boils down to 4 pillars. 1, scale the vision backbone. Don't skimp on the eyes. Make them as smart as the brain. 2, fix the input. Use dynamic tiling for space and multi-stream for time. 3, align the pipeline. Walk the model from basic matching to complex conversation. And 4, automate the interface. Use vectors like COOP to solve the prompt bottleneck.
It feels like we are moving from academic curiosities, cool papers that generate trippy images, to robust production systems.
Exactly. We are moving past the, wow, it made a picture phase into the, this system understands the world reliably enough to do work phase.
That is a massive shift.
It is. And if I can leave you with one thought, go back to what we discussed regarding COOP and TPT. We are effectively automating the interpretation of reality.
How do you mean?
Well, we aren't just teaching machines to see. By using these learnable vectors and test time tuning, we are teaching them to tune their own questions about what they see. They're adjusting their internal perception filters to minimize uncertainty, independent of us.
That sounds efficient. And a little spooky.
It raises a big question. What happens when the model's visual interpretation, its internal mathematical certainty about what is in an image, becomes more consistent and accurate than human perception? If the AI effectively sees better by asking itself questions we can't even articulate, whose version of reality do we trust?
Wow. Okay, on that slightly terrifying but fascinating note, we're going to wrap up. A huge thank you to the authors of Scaling Vision Language Models for the source material.
It was a pleasure to analyze.
And thank you to you for taking this deep dive with us. Keep your eyes open. We'll see you next time.